Hello, in this video, I am telling you magnetic properties of matter. So matter shows two type of property, just like non-magnetic material and magnetic material. So non-magnetic material no shows no effect of magnetic field, but magnetic material are of three type: diamagnetic, in paramagnetic and ferromagnetic. It is प्रतिचुंबकीय, अनिचुंबकीय and लोहचुंबकीय. So diamagnetic repel in opposite direction, paramagnetic attracted in external field, and ferromagnetic attract strongly in magnetic field. So term related to magnetization of a material. So first of all, we will discuss magnetic induction. It is denoted by B bar. So number of magnetic field line passing per unit area perpendicular to surface in the external field. So unit is 1 Tesla is equals to 1 Weber upon meter square. 1 Newton upon meter is equal to 10 power 4 Gauss. And then second is intensity of magnetization. It is I bar. So magnetic dipole moment per unit volume. So I is equals to m upon b. So unit is m is equals to nia mp meter square, and b is equals to meter cube. So I is equals to m upon b. So we will find out ampere upon meter. Then I am telling you magnetic intensity, magnetic field strength H bar. So field of external magnetic field. So it is V is equals to mu naught I plus H. Its unit is A upon M. And for no material, that is vacuum, I is equals to 0, B is equals to mu naught H, and H is equals to V upon mu naught, and V is equals to mu naught Ni, Ni is equals to V upon mu naught, because small n is equals to capital N upon L. So capital H are our Ni, or capital N upon L are our I. Now I am telling you magnetic permeability, and we will define it by mu. So degree of magnetization, it is the ability of material to permit the passage of magnetic field line. Okay, so it is mu is equals to B upon H, and unit B is Weber upon meter square, and H is meter upon area upon meter. So the unit of mu is Newton upon ampere square. Okay, so then it is called Weber upon a meter, Weber upon area meter. Okay, so because we know that L is equals to mu naught N square A, so after we will put down here, then we will find out relation between mu naught is equals to H upon M. Okay, now I am telling you relative permeability. Then mu r is equals to mu upon mu naught. This is a dimensionless quantity. So for non-magnetic, mu r is equals to 1. For diamagnetic, mu r is less than 1. Paramagnetic, mu r is greater than 1, and ferromagnetic, mu r is greater than 1. Then I am telling you magnetic susceptibility. It is GIM. It is a measure how easily a magnetic material get magnetized in magnetic field. So GIM is equals to I upon H. It is a dimensionless, and mu r is equals to 1 plus GIM. So for non-magnetic it is 0. For diamagnetic it is negative and small. For paramagnetic it is positive and small. For ferro it is a positive and large. So now we will discuss relation between B and HI. So B is equals to mu naught I plus H, and when we divide both sides by H, we will get this: mu is equals to mu naught 1 plus chi m. And if we divide it, we find out our final answer: mu r is equals to 1 plus chi m. Here mu r is relative permeability, chi m is magnetic susceptibility, and epsilon r is 1 plus chi e. It is a electric susceptibility, it is a relative permittivity, it is a dielectric constant. Okay, now we are moving to another thing, classification of magnetic material. So we will discuss diamagnetic material. In Hindi it is called Pratichumki Padarth. It is a universal property. So magnetize freely opposite to magnetic field. GIM, it is a temperature independent. So magnetic dipole moment, orbital plus spin plus nucleus. So orbital is small, spin main, and it is also small. So pair electron of opposite sign spin. So total magnetization is net is 0. So you can figure it that m is 0 and m net is 0. So that example you can learn this. Hanji, bismuth, sona, chandi, namak, para. These are diamagnetic material. H, hydrogen, nitrogen, zinc, bismuth, aurum, argentum, NaCl, and Hg. So these are diamagnetic. Now we are moving to paramagnetic material. So these are anuchumkiya padarth. So magnetize freely in same direction of a magnetic field. So output most paired, unpaired electron. So m is not equals to 0. M is not equals to 0. So I is equals to m upon v. M is equal to I upon h. So Curie law is I is inverse directly proportional to h upon t. And when we put C, so then we will find out m is equal to C upon T. Here C is a Curie constant. So you have, this is a trick, CrPt, Mn, Na, Al, Cu, Here Cr is chromium, platinum. Now we are moving to strong magnetic field. Ferromagnetic material, it is a strong magnetization. Then magnetize strongly in the direction of magnetic field. So there are lots of unpaired electrons. So complex interaction, m naught is equals to 0. Here we use Curie-Weiss law. M is equal to C upon T minus Tc. Tc is Curie temperature. The temperature above is ferromagnetic become a paramagnetic. So this is a Tc. Curie temperature, that is a paramagnetic, that is a ferromagnetic. Okay. So at this temperature, ferromagnetic become paramagnetic. Now this is the trick, that Ficoni magnetite. So ferrum, cobalt, nickel, FeCO3. Now diamagnetic, Xm is negative and small, and it is a temperature independent. So you can watch that it is a straight line. But for paramagnetic, you can watch that Xm is C upon T, that is a Curie law, and Xm is inversely proportional to 2. So Xm is positive and small. So you can find out that it is inversely proportional. That is, so this figure is downward, inversely proportional. Then we will move ferromagnetic. Then Xm is C upon T minus Tc. Xm is positive and small, positive and large. So you can figure that this is the graph. So this is a Curie temperature. So ferromagnetic become paramagnetic after when we move from Curie temperature. Now this is a antiferromagnetic material. This is MnO, MnS, Cr2O3, NaCr. So these are opposite direction. Then this is the graph that is a for temperature. It is called nil temperature. Before the temperature point, magnet material are antiferromagnetic. Then after the temperature nil, it is a paramagnetic. Now we are this is a ferrimagnetic. So in small quantity in opposite. So it is a iron oxide and metal oxide. Now we will move hysteresis curve and loop. So you can watch it curve. This is a between V and H, and you can show this graph. So this is retentivity and this is a coercitivity. Then it is a hysteresis loop and curve. So ferromagnetic material. Here Xm is positive and large. So how easily magnetic material is magnetized? This is so. So hysteresis loop area, energy loss per unit area in one circle. Okay, now this is ferromagnetic material. It is a hard and it is a soft, and it is a steel and it is a soft iron, and it is AlNiCO, Alnico, and it is a permanent magnet. Here is a mu metal, here is phi v is equal to 0, it is a temporary magnetic and electromagnet. Now it is a permanent and temporary. So for permanent it is x xi m is decreasing, for temporary xi m is increasing. For mu permanent is mu is decreasing and mu is increasing for temporary. So retentivity increase for permanent but retentivity decrease for temporary, and coercivity increase for permanent and decrease for temporary, and hysteresis law increase for permanent and decrease for hysteresis. So you can watch this figure. This is a steel and this is a soft iron, so you can see this quantity by this figure. Okay, note: in general, retentivity for temperature magnet is small, that of permanent magnet, but in case of soft iron, retentivity is higher than that of steel. Okay, so these are all the things in for today. Okay, so thank you.